Okay. So moving on, new stuff. So remember, Google keeps both the raw page data that it gets, and it also keeps data for pages from pages that have been extracted, right? So if it wants to revise its algorithms, it needs a pool of page data to find things that it might not have already extracted. If it says Google wants to use some new feature from pages, it needs to go back through and see, hey, is that feature actually there, and how are we going to implement this? On the other hand, if Google is actually doing retrieving search results, it wants to be able to do that very quickly. And it doesn't make sense to hold copies of all those pages when what? When it would be much faster to have that data already extracted, right? It doesn't want to look at the web pages for every search, dig all through them and see what words are located where. It's nice to have that information readily available. Okay, so we talked the other day, right? We talked about how Google has this hierarchical system, and the big takeaway from that is that number one, the index is really big. Number two, it doesn't make sense to store every part of the index at every data center because a lot of content is only going to be of interest in limited parts of the world. For example, pages written in Japanese are likely to be not much interest to anyone outside of Japan, right? There's some pockets of Japanese in South America and on the West Coast, but you get what I'm saying. Anyway, so it wouldn't make sense to store the entire index completely at every data center and go through all the work of keeping it up to date. It's better to just keep the information you need where you need it. You can save a lot of money that way. Okay. So again, any particular data center is going to store pages that are expected to be of greater local interest. And the big things for that, stuff like pages about local places or about local people. But the big one is just language, right? That's kind of the default setting of where Google figures out where to store a page. If the page is written in Japanese, it's probably going to get immediately stored at a data center near Japan. If it's written in English, chances are, American English, chances are it's going to get stored in one of the North American data centers. If it's written in UK English, probably go to, a data center near the UK. So you get the idea. Other things, different kinds of information are, of course, more relevant to smaller areas. So with queries like asking about the weather or about local events, the assumption is always going to be for this location. For example, there are two cities in the world named York. Well, there are at least two. There's York, Pennsylvania, and there's also York in the UK up near Scotland. Okay, and they're very different pools of people there. So if you are near Pennsylvania for some reason and you're searching for York, chances are you're going to get information about the local city in Pennsylvania named York. Whereas chances are if you're up near Scotland and you do a Google search for York, probably going to get pages about the city of York up that way. Other things, anytime you ask for just weather, Google says, oh, if you're asking about weather, chances are you mean whatever zip code you're in. So if Google has a data center in Chicago or near Chicago, it's going to keep pages about weather forecasts for zip codes near Chicago, right? That's the sort of stuff that it'll keep there. Anyway, and again, when necessary, pages that aren't stored locally can be retrieved from other data centers, or if Google has some, comes to have some big database where all these things are stored, could be retrieved from there. Basically, could be retrieved from non-local sources. All right. Second thing, just like Facebook, Google also has to deal with the long tail popularity problem. All right. So we talked about that with pictures. What's going on? Is this very important? Shall we all just let you, what's going on? Do we need to let you take a minute? No? Okay. Like I said, phone messaging is a thing. You can text each other. All right. Okay. Has anyone here ever heard of a zip distribution? Nobody? Oh, well, that's okay. A zip distribution is basically a kind of frequency distribution. And what it looks like is something like this. So there's all sorts of different variations on it. But the idea is you have some measure of frequency, how often something shows up, and then some measure of rarity. So for example, if you're trying to construct a zip distribution about what words are more often seen in, American English, you might see some very common words like the, or this, or he, or she, or they, or it, or and, or is, right? Words like that come up an awful lot. And it's hard to write a sentence that, probably doesn't contain one or two of those. So these are very frequent words, very common, right? On the other hand, there are some, less common words like truck or, I don't know, sunflower. These are words, they certainly do appear, but they don't appear very often, right? So when we talk about the long tail, what we mean is simply there are some things that are going to show up a lot, and these are the sort of things roughly that Google would cache. So if we're talking about search results, if we take each of these words to be like a query going into Google, these would be very common queries. And because they're so common, Google's probably going to cache them. These ones are ones that are going to happen, but they're not very common. And so it's not cost effective for Google to cache them in RAM because RAM is expensive. But Google still has to design its system to deliver results matching these pretty quickly. All right, so it's a lot like Facebook's haystack problem with delivering photos. Okay. Now, just as a factoid, of course, the majority of searches on Google at any given time are for current events, right? Things like whatever movies are popular, or give me the current weather, or whatever's in the news these days, stuff like that. That's most of what Google sees. But there are a fair amount of searches for rare or even unique things. So the last stat I have on this is from 10 years ago. But from 10 years ago, even 15% of the searches that Google was processing, 15% were ones that Google had never seen before, right? So kind of like once in a lifetime things. Some of those are going to be like different combinations of names and terms, right? Like if you're looking for a particular person in a particular city or at a particular university, things like that. Yeah, you might be the first person to look for that. Other things that might be rare are misspellings, right? Because misspellings tend to be kind of random and unpredictable and unique. So, but anyway, Google does have to deal with a fair number of really unique searches, right? So it's not like they can cache everything. And again, even if Google could cache everything it's already seen, based on this, 15% of the searches, there's no way Google could cache those because it hasn't ever seen them. Anyway, so conclusion, Google can optimize performance by continuously updating and caching popular searches, but the older, less popular ones also can't be ignored. Just like we saw when we did some checks with rare and common words, common searches might get a whole lot of pages. Rare searches, even involving like sets of the weirdest words you can think of, still are going to come up with, hundreds or even millions of pages. It's crazy. All right. Now, let's talk about the task division. So for the task division, I'm going to start off by drawing a picture that then we can reference for most of the rest of the lecture. All right. So the first thing that happens, somebody sends Google a query. Hey, could be you, could be me, could be somebody else. But somebody sends Google a query. Now, one of Google's systems, right? The local data center gets it. And the question it can ask is, will it handle it locally or not? Right? And so we don't know exactly the special sauce of how this happens. So one way to look at this is like, say, there's a first pass, something basically, look at the language of the quote, right? Look at the language of the search is an obvious one. Now, if it's in a totally different language, chances are it's going to get kicked to a different data center, right? So, for example, if you type something in French in Google, it's probably not going to have it cached near Chicago. There's not a large French-speaking population around here. It's probably going to get kicked off somewhere else. So, if the language is compatible, we say no and yes, because we're using flowchart notation now. If it's no, then Google will ask another data center, right? Basically going to forward that request to another data center, and then eventually get the results back, send it back, and, you know, kick it back to the person, right, and say deliver results. We'll do that here, deliver results. Okay, but for the moment, let's assume that, in fact, this data center has looked at the text and says, okay, this is something we can at least consider fulfilling locally, right? Maybe we have the exact pages and index entries, maybe not, but at the first pass looking at it, yeah, there's a good chance we can do this. So the next thing that's going to happen, actually, is Google is going to put it through a term check. All right, it is going to say, what are the terms that we are going to pull from this search query, right? So if you enter in a long string of text, Google has to look at things like how are they going to be grouped, and are there any misspellings in there? Google has to feed that to the next stage. So the next stage is going to ask, and we'll do another flowchart diamond here, and we'll ask handle locally. And either it gets handled locally or it doesn't, right? Once again, if it doesn't get handled locally, kick it off to some other data center, say, yeah, we can't handle this, you know? Or if we say yes, then whole page data, right? So what's going to happen is Google's going to look at the index and it's going to say, well, do we have index entries for these terms that we pulled out from this query? If we have it, great, we can work with that. If we don't have it, we'll have to kick that query off to somewhere else. Okay, and we're going to ignore the weird hybrid case where maybe the data center has, you know, some index entries for some of the terms, but not all of them. Maybe it has to kick some of them somewhere else. All right, so if it decides it's going to handle it locally, then it's going to have to pull that page data out of its databases somehow, and then make it undergo a ranking process, right? And the ranking process is going to simply look at, you know, how should we arrange these search results? What's going to go first? What's going to go last? What's going to be the cutoff? Are we going to send back 100 or 200 results or something else? Let me draw a curvy arrow for this. Okay. Whoop. Damn it, Beavis. All right. And we deliver the search results, same way. Okay, so this is the big picture of how it happens. And we'll dig in a little bit to all of these polygons, but questions on this at this point, bearing in mind that some of this is special sauce and Google isn't really going to give us all the details about it. Does this make sense? Is this a good framework? We're happy? Anyone confused? All right. I do sometimes get, you know, students who say they're confused. If you look at some of the stuff that's been written about me or the course or whatever on Reddit, there's like people who like, I've been here for 4 lectures and I still have no idea what the course is about. And I'm always like, maybe you weren't paying much attention. I don't know. I'm doing the best I can. But if you have questions, by all means answer. I also say, like, if you're here for 4 lectures and you have no idea what's going on, shouldn't that be like the point where you raise your hand and maybe ask and try to figure out what's going on, right? Just saying. Okay. All right. Okay, well, let's get back to it. So again, when Google gets a search query, and we're going to assume the system has determined it's going to be handled locally, first it's going to check the cache, right? Are those search results already available in the cache? If so, that's great. No further processing required. Otherwise, you got to process the search, right? You got to break it apart, figure out what terms you're going to use, figure out where those pages are, rank the pages, deliver the results. Okay. Now, as far as the indexing system, it's built around 3 server roles, right? There's basically 3 different kinds of servers that Google uses. Number 1, there are index servers that hold the index entries, right? So there are machines that hold the different segments, you know, the lists of, for this term, it's found on these pages. For this term, it's found on these pages, right? Those are the index entries. There are also document servers. Document servers hold complete web pages and can be used to extract data to be stored to do faster ranking, stuff like that. Okay? And then again, last I checked, and it's been a few years because I don't dig through this stuff that often. But the last time I checked, the document servers were also responsible. So when a Google bot looked at a page, it would send that data to a document server, and then the document server, which had the page, they would scan through it and send that data to the indexing system so that the index could be updated, and it would send the extracted data to another system where page data extracted is stored. They may be doing it at a slightly different way at this point. That's why I'm kind of not focusing too much on that. But the last I checked, the document servers, were responsible for receiving the pages and then, extracting the data and sending it elsewhere. And the third set of servers was spelling servers to check for alternatives, right? If you type in something wrong, Google wants to try to identify that and tell you made a mistake. So the process following a query is, first of all, at some point, Google is going to have to figure out what index entries correspond to the query you typed in. So it's going to have to parse it in some sense. It's going to have to break it into pieces. We'll talk a little bit more about that. But if you enter in a string of like 6 or 10 search terms into Google, it's not going to have an 8 or 10, word index entry. It's going to have to figure out, do we break them all apart one at a time and have, say, 8 different index entries we're using, or are there 4 pairs of index, of terms? How's that going to work? And of course, it's going to look at, not only exact matches, but ones that have similar meaning. And again, with the spell check, try to identify what those possibilities are as well. Then once it's figured out exactly what terms it's going to use, Google is going to retrieve the web page data based on those search terms and ultimately deliver ranked matching results. All right. Now I do have an early paper here. I know I got to go to screen. Okay. So this is, you may recognize the names of these fantastically wealthy billionaires. This is an early paper they did explaining Google circa 1997. Anyway, if you're interested, by all means read this. I mean, you don't have to understand all the math or anything about it. But the core point here, I want to talk about a couple things. Number one, storage statistics, right? So this is an early version of Google, and they did it with about 100 gigs of data. Now, these days, 100 gigs of data is not very much, right? It'll comfortably fit into a small corner of your hard drive, especially if you got one of the big ones, like a 2 or 4 terabyte one, then it's just, whatever. There are literally many video game installs that require more data than this. There was a, there's a Guardians of the Galaxy one like a year or two ago that I heard had a 250 gig footprint on your hard drive. So, this is less than one game. But 1997, this was a lot of data. In 1998, I got my first desktop, and it had a 6 gig hard drive. And 6 gigs was pretty big, right? It wasn't the biggest available. It was pretty big. And I'm going to say that, that total of data is something around 30 or 50 hard drives worth of data. So it's not a trivial thing to set this up in 1997. All right. Anyway, so in that kind of distributed system, Google set this up. They ran a bunch of search queries and looked at how much time it took to find the matching results. So Al Gore, he was vice president for a big chunk of the 90s, but his name doesn't appear on that many pages. Because, vice presidents, when they're actually vice president, they kind of tend to be forgotten, right? It's kind of like, who is that guy? Or who is that woman these days? But anyway, so it didn't take that long to run through the query and, deliver the search results, right? Because there weren't that many pages. And when it was cached, it went down to a super fast time. Now here it's split up into CPU and total time. CPU is how much, CPU cycles the computers are doing. The total time, the rest of that is pretty much retrieval from the hard drives, right? And hard drives aren't super fast. Other terms that are on more text or, harder to find, whatever, the system isn't optimized for these oddball requests, could take substantially longer, right? But still, you can see that when the same query is repeated, you save a little bit of time on the CPU, not that much, right? So 1.77 to 1.66, 0.25 to 0.20, but you save a lot of time versus the hard drive, right? So here it's almost 5 seconds to pull all of that from hard drives, but if it's stored in RAM, we're quarter of a second. Anyway, So they were doing caching right from the start, and yeah, I guess that's the point. Okay. But of course, the system is very different now. You know, the hardware is very different, and the mechanisms for searching are very different as well. Okay. So if you're interested, by all means, you know, look at that at some point. Now, the index servers. So index servers are divided into clusters divided by grouped into clusters divided by language. So at a given data center, there's probably going to be more than one language spoken in the vicinity, right? If you have a data center in Western Europe, for example, maybe one in Belgium, they're going to have, you know, the variants of, you know, the languages Belgians speak, Flemish, Wallonian, I don't know. They're also going to have, you know, nearby French, they're going to have Dutch, they're going to have German, they're going to have probably Italian, probably English, you know, they're going to have a lot of different languages. Europe's packed kind of tight that way. If you have a database, a data center near Chicago, sure, it's going to be mostly English, but there's probably going to be some sections for Spanish and Polish as well, because, you know, Chicago. Anyway, so it has different sections of servers, you know, divided by language. Now, for English alone, there are probably several 100,000 terms, right? There are over 100,000 words in English. And then you tack onto that things like names and places and numbers and other stuff, then, you know, the number of things starts spiking up. And anyway, each of those might be associated with millions of pages. So if you do the math on that, if you have, say, close to 1 million search terms, and maybe each search term on average is found on 1 million pages, that's 1 trillion things right there. So even if all you're doing is tracking some code of where to find the data, like maybe some 16-bit code, that's 16 terabytes of data for just tracking where the stuff is. So again, the key takeaway, these indexes are way too big to be on single machines. They have to be broken up across many machines, right? So the next point, index divided over many, many servers. Now, because it's already broken up, that means Google can say, oh, the index sections are already set up to get processed in parallel. So if a query comes through, Google can just send the relevant part of the query to all of the machines that have some part of the index entry. Again, queries not in the local language most likely be forwarded to a different cluster or a different data center entirely. Anyway, so when Google gets a search query, the system first has to perform some semantic analysis to figure out which index entries correspond to search terms. So if you enter the terms 17th century astronomers, even though you haven't entered the term Galileo, Google's going to recognize, oh, 17th century astronomers. Here are some names that belong to that set, including Galileo. We can pull that, right? Or if you enter in something like Chicago Cubs players, Google can figure out, oh, here are some guys who are or have played for the Chicago Cubs. We can pull those pages. Anyway, and once Google has figured out which index entries the query is going to involve, it can forward the query to the appropriate servers that hold the appropriate parts of the index. All right. Now, this is some detailed stuff. Not going to ask this about the exam, right? So this is kind of starting to get into the weeds a little bit. So data centers have tens of thousands of servers, right? And they're already organized into tiers, into groups, doing the same kind of task to handle queries in parallel. But index entries themselves tend to be very large, or at least some of them are very large, and may be broken into shards, into fragments that are stored separately on different machines. So if you have one index entry that contains, you know, like for sports, contains billions of pages, you're not going to put all of that data on one machine, right? You're going to break up that index entry and have segment 1 or shard 1 on one machine, shard 2 on another, shard 3 on another, and so on. Now, a couple tricks Google uses to process queries faster. Number one, parallel operation, right? If you can divide a big task into many small tasks can be completed a lot faster. So that's one way to return the search results faster. And Google has a trick there. If you have a page that's stored in multiple tiers, for example, you are doing a query that involves, you know, multiple search terms, the pages that are involved are going to be on the same shard number in any tier. So if you have a search query that involves, you know, one page that's in shard number 3 of tier 1, that page is also going to appear in shard 3 of tier 2 and shard 3 of tier 3 and so on. And what it's basically like is traffic lanes on a road. So Google wants to, be reasonably efficient, very efficient, about how it's processing these requests. And the best way to do that is to be able to only involve a small section of the data center for any given query. And the way they do that is by having, pages appear in the same shard in any tier, without getting into the math of how they do it. The other question is how many machines should handle a query, right? So you can understand that going from one machine handling a big problem to two machines each solving half of the problem, you're going to about double the speed of the process, right? But there's also a little bit of friction built in. There's a little bit of calculation and networking involved in breaking up that query into pieces and then restoring the results together at the end. So you do eventually have diminishing speed returns. So, if you're breaking it up into 10 pieces, yeah, you get closer to, you get close to 10 times faster. But the more machines you add on, there's going to be this little extra bit of working time involved in breaking apart the query and restoring the results, combining the results at the end, and the network traffic involved in doing that. And it's going to add on a little bit of time. So at a certain point, it's not really worth the bother breaking it up any further. Okay, so Google tries to optimize that as well. It tries to, any query that's a big problem, yeah, it's going to break it up, but it's only going to break it up so far. Okay, but like I said, that's kind of advanced stuff that I'm not really going to see on the exam. All right, other stuff, index structure. So remember, all of this stuff that we've been talking about is kind of Google's special sauce, so they don't talk about a lot about the details of their implementation. And even if I were like a Google engineer, I would probably be bound to secrecy to not share any of those details, so it wouldn't really help. However, yeah, what we can do is look at some of Google's patent documents. So this one, query scheduling using hierarchical tiers of index servers, which, believe it or not, you ought to be able to make a reasonable guess about what that means. Sounds complicated. It kind of is. All right, but query scheduling, right? Well, how you're going to process the query and in what order and sequence and how you're going to arrange it, stuff like that. Hierarchical tiers, okay? So it goes through one process of machines, right? That's a tier, goes through another process of machines and so on. And we've talked about what index servers are, all right? So basically, this is how Google uses its hardware. A search query comes in. How does Google figure out what index entries it's going to correspond to? So it's a big document. I certainly don't expect anyone to read it all, but there's a couple points we're going to bring in here. All right. So first thing, this isn't one of the couple points, but just the idea, if somebody enters in a search query, right, there are different ways to break it up. For example, somebody enters in the words New York restaurants, right? There are different ways you could break that up. It could be new and York and restaurants, or it could be New York as one semantic unit and restaurants, or it could be new and York restaurants as a semantic unit, or the whole thing could be one semantic unit. And Google's a computer system, not human, so it just doesn't know. It's got to kind of look at what things people are looking for. All right, so that's the basic problem. Now, if we scroll down a little further, we can find, oh, here we go. The quick brown fox jumps over the lazy god. Now, you can see with a longer stretch of terms like this, there are a lot more possible combinations, right? There are many different ways this could be broken up, right? Google says there are 250, right? Oh, okay, well, that's fine, whatever. I don't know. This is identification server 250, so that's not really the 250 there. But there's a bunch of different ways this could be separated. But one thing that Google knows is that people tend to enter in the same word, related words sequentially. Okay, and so here's the final thing. So that was one. The point is Google assigns a score to different combinations, right? Here, this is all quick brown fox jumps. Google has a scoring method for figuring out how much the different terms should be together. And if we're looking at the sentence, I guess we'll roll up for a second. If we're looking at that sentence, the quick brown fox jumps over the lazy god, we can look and say, well, as humans, brown fox is probably a plausible combination. Lazy god is probably a plausible combination. Quick brown fox, maybe a plausible combination. Maybe the and the, strike those. Jumps over, maybe that's a combination. Okay, so there are different ways, but you can also say that, what shall we say? Quick brown fox jumps over. I don't know, that doesn't sound right. And so Google has a scoring process for how to figure that out. And I'm just going to do one last thing here. They talk in a lot of stuff. I'm just going to find Ethiopian. Ethiopian. There we go. New York Ethiopian restaurants, right? So the possible phrases there could be, New York plus Ethiopian restaurants, or, any of these other combinations down here. And Google needs to figure out which one of those makes sense. And basically, a lot of what it looks like is some assumptions on how people are going to write queries. And number two, any semantic units that are actually present in its database. So for sure, New York is going to be present as a semantic unit in Google's database. Quite possibly, Ethiopian restaurants will be present as a semantic unit in Google's index. And if Google finds that those two are there, it can kind of look and say, oh, these are the two things that actually appear as units in the index. This is probably where we want to start. Okay, but this is kind of an old document. It's when is this? This is from 2007, so it's been, they've updated their system since then with all these semantic things. Semantic modeling was just starting to get a little traction then. Okay, so key takeaway, somebody enters in a big search query, Google's going to decompose it into likely phrases, which is a lot better than considering all possible combinations of the terms. Okay, and one of the big things that Google doesn't want to involve every machine in a data center with a query. So it has ways to group the pages together. That's the big thing. So if a query comes in, Google wants to be able to say, not scan every page in the entire index to see if everything is there. Google wants to very quickly say, oh, the page is here, they're for a couple of index entries. We don't have to search through the whole database to find what we're looking for. Okay. Excuse me. Next thing, document servers. So document servers for Google, their big thing that they do is they store raw page data, right? Page data that has not been, extracted for later use. So Google has tens of trillions of page documents, multiple copies of each. And again, these document objects, because they're web pages, they don't have a definite structure, right? We've already talked about how web pages don't have a fixed structure. Doesn't make sense to store them in a relational database. Second thing, this system is very, 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 very large, right? If you have trillions of page documents, there's no possible way you're storing that on one normal machine. It's just too much information, right? A trillion bytes is going to be a terabyte, and if every page has many, many bytes of data, you're going to need many, many hard drives to store that data. Okay, so basically, when a query gets processed by the indexing system is going to find the matching documents, right? It's going to analyze the relevant variables that have already been extracted from the pages. And Google uses basically a multi-stage set of page ranking. So the first thing it's going to do is Google's going to just look at the strength of the match. So Google say, okay, here's maybe the term is shoe sale downtown Chicago. And it's going to figure out what phrases it's going to use, like maybe shoe sale and downtown Chicago. And it's going to look at where those terms show up on the pages. If it finds a set of pages that are pretty close to each other and in terms of where the terms are and how they're located, if they're in the same order, if they're in the title or headers as opposed to ordinary text. If it finds a set of pages that are reasonably equivalent and near the top of the search results for best matches, then Google has to dig a little deeper and figure out whether, oh, this page, it has all the terms, but it also has, web objects like drop-down menus and currency symbols suggesting they're actually selling shoes. As opposed to this is like an advertising notice about a shoe sale and has a bunch of other kind of junky, irrelevant text in there. So the first one that's actually like a retail site is probably a better match than this other page that just happens to have those terms. Okay, so it does multiple rounds there to somewhat simplify the process. All right, Google stores web pages in their original form and separately with the data extracted. So reason why Google stores some of these documents in their original form, again, if Google wants to update its algorithm or try some, alternate things, if it says, yeah, we know we already have hundreds of variables in our complicated algorithm. We want to add a few more, or maybe we want to change the weighting on some of them or include some new features somehow. It's nice to have all that original data already on hand so Google can do the testing with that. Otherwise, anytime it wanted to, consider a change, it would have to make a special effort to pull in a whole bunch of data and store it somewhere, which, again, they'd have to store it somewhere anyway. And because web pages have no inherent structure, some kind of NoSQL system is the option you want to use, right? Because it's pretty efficient in terms of storage space. Data extraction, on the other hand, makes all important variables for matching and ranking available immediately, right? You don't have to dig through the raw page data and see if the terms are there and how they're located. You want to have that work already done because, a lot of queries come in repeatedly. So because of that, a uniform structure compatible with relational database systems is kind of the way to go. Google can say, for any page, we can look at the same kind of data. And there it is. So if every page Google's looking at the same kind of data, then the relational database model makes sense because every record gets the same set of columns. However, there are some interesting extensions that Google makes. So Google has a system called Bigtable. Bigtable is basically an extended relational database model. And we'll talk about that. But the objects, the web pages get stored as sparsely populated tables of rows and columns with a timestamp. So we haven't talked about sparsely populated, so you shouldn't know what it is. That's okay. We'll get that on the next slide. But basically, every row is going to be a page with a timestamp attached. And the timestamp is just if somebody wants to get the most recent version of a page or a slightly older version, or Google wants to know if it should roll back to a slightly older version, whatever. Google has that timestamp data available. Well, let's talk about Bigtable. So Bigtable has a few things. Number one, rows that are related, so pages that are related that tend to come up in the same queries a lot, Google tries to store them physically near each other in its system, right? So on the same hardware. And the nice thing about doing that is then queries don't need to search the whole database, right? If you say, well, here's a set of pages we're going to look at, and they're all on this machine, that means Google doesn't have to scan its entire server tier trying to find those pages. It knows if it finds one of them, it finds them all, so it really only needs to look at one machine. Second, Google has this concept called column families. So imagine that you want to track web page data, but one of the things you want to track is images. Now, of course, web pages may have dozens or hundreds of images. And in the relational database model, where every row needs to have the same columns, it doesn't make sense to have that many, single image entries, single image columns. So what Google does instead, there are some kinds of data, there tends to be multiple ones, it tends to be a list of things. Instead of actually storing all the things, like all the images, Google will just store a link to a list. So instead of having a separate column for every image that a page might have, Google will have a column family for images. And then if that page has images, that entry will contain a link to some other part of the database where a list of those images is stored. So it allows the pages themselves, the data, to still follow the relational database model, because every record has the same things, but it also allows for the fact that different pages might have different quantities of those things. And the last one is sparsely populated. So Google's ranking algorithm is super complicated, has literally hundreds and hundreds and hundreds of variables that it looks at, and it's inevitable that a lot of pages aren't going to have some of those things that are being looked at. For example, you might have a page that only has basic text, no web objects to speak of, right? Or you might have a non-retail page that has no real reason to have all the features and attributes that a retail page might have. So because of that, and because Google doesn't want to store, hundreds of zeros for its many, many pages, Google also allows rows to be sparsely populated. Basically, if a page has no data for a group of fields, for a group of columns, Google can just put a marker in that field that says, nothing to see here for an entire set of fields. And that saves a lot of space as well. Okay, because again, when you're talking about tens of trillions of web pages, right, you don't want to have your database filled with a lot of zeros saying nothing to see here. So Google has a way to compress all of that together. All right. Last thing, spelling servers. So what spelling servers do is they receive original search queries, try to identify misspellings, we'll talk about query rank in a minute, and then return a list of likely alternatives that might be considered. So the way this was first, a lot of people first saw this was something called the Google Search Appliance. So Google Search Appliance was basically a little piece of hardware that kind of looked like a server, and basically you could store many documents on it, right? 10 million or more, depending on the size of the documents. And the problem with document storage in a large organization is that there are always going to be misspellings, right? You don't want to have somebody miss a document because somebody entered in, a word that, was not exactly what is there in the document. So Google also wants to consider some alternatives. Where this happened in real life. So you guys vaguely remember in 2016, there was a thing with Hillary Clinton and emails. Yeah, vaguely, yeah. And her people deleted a whole bunch of them, right? And depending on how conspiracy minded you are, you might think either with good cause or, oh my God, what was she hiding? But we're going to skip that whole thing. So she had her people delete a big batch of emails right from the start. But then a few months later, you may recall a few hundred emails actually popped back up, right? There were emails that were missed. And everybody's like, what? How did this happen? Well, what actually happened with those is that whatever words that her people had been using to find which emails to delete, they had actually misspelled some of those words in the emails themselves. And that's why they didn't show up in the search. So it was things like, Hillary with 2 I's and stuff, you get the idea. So misspellings in the emails themselves, which when they did a closer look through all of it, they eventually found some of the ones that the first pass of deletions had missed. And that's the same sort of idea. Now, for what it's worth, the Google Search Appliance, you might find a few out there in the real world. I'm not saying nobody uses them, but Google doesn't really support them anymore. They wound down about 5 years ago. And, Google, of course, just wants people to go to the cloud. So, there's that. But for over 10 years, Google has corrected user spelling. Sometimes it's going to correct things that are definitely wrong, right? Or almost definitely wrong. Like a search term with no index entry or very few matches. For example, if you spell UIC with, 3 U's and a W, that's probably not in there anywhere. Sometimes, of course, it could just be correct but unusual words that are very similar to popular search terms. So, for example, there's the famous actress Charlize Theron, and suppose you have a friend named Charlie Theron. Well, if you and Charlie, he goes by Charlie. If you type Charlie Theron into Google, I guarantee. All right, let's try it. I'm going to see. I guarantee though you'll get. We think you Charlie Theron. Yeah, boom. There you go. Right, because. Who's this Charlie Theron? Nobody ever heard of. You've heard of her though, probably. Okay. Anyway, the way this works. Sorry, it's kind of a hassle. I'm not seeing the same. I'm not seeing the same view you are. So, the way it works is, first of all, Google decides on the query rank of any term, term or group of terms that is pulled out from your query. And it's better for terms that have high frequency, that show up in searches a lot, and are rarely revised. So revised means, imagine if you actually were trying to search something about Charlize Theron, and you typed in Charlie by mistake. Well, then you quickly go back and fix that in the days before, this sort of spell checking. But that's what we mean by rarely revised. So candidates that are going to be corrected tend to, number one, have a low query rank, and or number two, very similar to a highly ranked query. So Charlize isn't quite the box office draw she was 20 years ago, but she's still making movies and whatever. She's out there. So I imagine she has a fairly high query rank, much higher than, say, Charlie, the equivalent Charlie. And again, similarity can be individual words, could be semantic units, could be observed from sequential searches, right? So if you try to search in for one term, and then you often find that people go back and revise it. So it's a similar thing. Like if you have an Alexa at home, right, an Amazon Dot, one of the things you may find with songs is that you ask it to play a song and it'll give you like some weird version or some alternate, some song with the same name by some other artist, and you'll say no, I want this other one. And so that's again same kind of thing, kind of revision, so that Amazon right off the bat doesn't know what you want to hear, right? But if you tell it often enough, it tends to figure it out. All right. So last slide. I know everybody's happy to get out, but okay. Now, one of the things we've talked about ACID properties, right? So a database that follows ACID properties, the nice thing about it is that it'll always give you the correct answer, right? That's the whole point of ACID properties. But for large systems, it tends to be way too slow because you have to jump through a lot of hoops and make sure everything gets processed sequentially. It can create some problems. And again, Google is very, very big. So let's talk about that. So first thing, as far as Google users are concerned, all pages, all search results, they're read only, right? Ordinary users don't go into Google and edit the contents of pages. So that means you don't have that same kind of problem like you would at a Bitcoin exchange, where people are going to try to edit things at the same time and take $20 billion worth of Bitcoin out. Instead, so Google doesn't really have to worry much about concurrency, because the only thing that's going to happen from the outside is people just looking at stuff. They can't actually do any damage. Second, when changes to the system happen, they're designed to get processed very quickly. One of the things that Bigtable allows, because remember, pages that are closely related tend to be grouped together. So when Google has a change to a batch of those pages, it can process them all fairly instantaneously. Doesn't have to search through the whole big database to find them all. It says, oh, I know that little cluster of pages is right here. I can edit that super fast. And third, because Google, for pretty much everything maintains duplicate copies, even if Google's doing an edit on one or two copies, that third copy is always going to be available. So just like Facebook used eventual consistency for people who liked such and such posts, Google can do the same thing for search results. And again, yeah, the risk here, people can get slightly different results from entering the same set of terms, either at a different data centers or even at the same data center, based on which set of pages they're looking at. But number one, perfection isn't really expected at Google. This isn't like withdrawing Bitcoin from, your online wallet. This is just getting some search results. People understand that it might not be perfect. You might get some junk in there. But number two, changes that most of the time, changes aren't going to happen. Even when changes happen, they happen really fast. And even if you're affected by a change, chances are the effect is not going to be substantial. There's going to be some edit on a page, but it's not going to, bring one page from like the number 1 spot down to number 55 so you never see it, right? Most of the changes that'll happen will be at the lower end of the search results that most people never see. Yeah, worst case, there might be a little shuffling at things at the top. Whatever, not that big of a deal. So again, that's the trade-off Google makes. Google doesn't say we absolutely have to give super perfect search results, giving ACID properties with the best information available. Google is willing to accept a small probability of occasional minor failures as the trade-off for delivering search results very quickly. Okay? That's all I got. That's the end. All right, it's been a hoot. We'll see you Wednesday. We're going over the Google Ads lecture, so you might want to read that document ahead of time. Okay. What you got? Okay.